So today we're going to dive into this really cool scientific mystery that's hidden in plain sight, right in the air we all breathe. It's a fantastic story about how a group of students, armed with a bunch of data and some machine learning, set out to solve a puzzle that actually has a huge impact on our weather and our climate. Okay, so that sounds like a riddle, right? Can a forest actually predict the weather? Well, in a way, yeah, it can. And the key is this invisible process that's happening all the time among the trees. And it's something scientists are absolutely desperate to understand and, more importantly, to predict. Well, the secret here is this phenomenon called new particle formation, or NPF for short. Just try to picture it. You got these tiny individual gas molecules floating around in the air, and then all of a sudden, they decide to team up. They start clumping together until they form brand new solid particles. Now, this isn't just some random thing. It's a really fundamental process that's shaping the very atmosphere around us. So, why should you care about these tiny new particles? Well, it's because these particles are basically the seeds for clouds. The more particles you have, the more potential you have for clouds to form. And that directly impacts everything from whether you'll have a sunny afternoon to major weather systems. But, this process also has a darker side. In cities, when these particles form from pollution that we create, it leads to smog, and that has really serious consequences for our health. Okay, so to crack the code of when and why this NPF thing happens, you need clues, right? Well, our story takes us to a research station deep in a forest in Finland, where there's this massive tower that is basically listening in on the secrets of the air. And this is it. This is the Smear 2 research station. Look at that tower. It reaches way up above the forest canopy, and it's just covered in instruments that are constantly measuring the atmosphere, 24/7. And it's from this exact tower that all of our data, our set of clues, comes from. So what exactly are these clues? Well, it's a whole bunch of different measurements. We're talking everything from radiation, like UV light, to your standard weather data, like temperature and humidity. They're also measuring specific gases, things like ozone and nitrogen oxides, and something called a condensation sink, which, to put it simply, is a measure of how many particles are already floating around. Every single one of these is a piece of the puzzle. All right, we've got the clues. Now it's time to bring in the detectives. And in this case, a group of university students were given a heck of a challenge. Could they teach a computer to spot the pattern in all this data and predict when NPF was about to happen? And look, this wasn't just some homework assignment. This was part of a term project and even a Kaggle competition. These students had to build a real, working machine learning model. Their mission, basically, was to create a digital detective that could sift through all those atmospheric clues and make a solid prediction. Now, what's really interesting here is that the challenge was actually twofold. There were two levels to this mystery. The first task was pretty straightforward, a simple yes or no. Did an NPF event happen on a given day? But the second task, that was a lot tougher. If the answer was yes, the model then had to figure out which one of three specific types of event it was. Okay, so how do you even start with something like this? Where do you begin? Well, the very first step is to just get your hands dirty and look at the data. You have to really immerse yourself in all those clues and hunt for any little hint of a pattern that might separate an event day from a non-event day. And you know what? Almost immediately a pattern started to pop out. Just as the students put it in their report, the days with NPF events just looked really different from the days without. And the biggest giveaways? The amount of sunlight and the humidity in the air. And when you dig in a little deeper, the data showed a really strong positive correlation with things like global radiation and UV light. That just means that lots of sunshine made an event more likely. And on the flip side, there was a strong negative correlation with relative humidity. So, to put it simply, NPF likes it sunny and dry. But here's the thing, just using the raw data, that's almost never enough. The students used a really powerful technique called feature engineering. This is where a lot of the magic happens in data science. It's the art of taking the basic clues you have and combining them in really clever ways, often using existing scientific knowledge to create brand new, way more powerful clues for your model. And this is where the students got super clever. They crafted these brilliant new features by mixing their data skills with actual scientific research. For instance, based on an earlier study, they transformed that condensation sink variable to make it more useful. They took humidity readings from a bunch of different heights and combined them into one single powerful average. And the most impressive part? They actually used a formula from a 2005 scientific paper to create a nucleation score, a totally new clue that calculated the probability of an event happening. I mean, this is where data science really meets atmospheric science. It's awesome. All right, so with these amazing new clues they built and a really deep understanding of the data, the students were finally ready to build their model and see if they could crack this case once and for all. Their final solution was actually pretty brilliant. It was a two-stage model. First, they used a simple but really effective model called logistic regression to answer that first question. Did an event happen, yes or no? And only if that model said yes, did it pass the case along to a second, more complicated model to figure out which specific type of event it was. So, how did it do? How did their digital detective perform? Well, for that first simple question, event or no event, the model was incredibly accurate. It got the right answer 89.3% of the time. That is a huge success by any measure. But what about that harder question? Yeah, when it came to identifying the specific type of event, the accuracy for that whole combined task dropped down to 68.8%. Now, that's still a pretty good result for sure, but it just goes to show you how much more difficult that second part of the mystery really was to solve. So here's the bottom line. The digital detective was fantastic at telling event days from non-event days, no question. But telling the difference between the subtle subtypes of those events, that was a real challenge. And it especially struggled with one rare type called Aya, mostly because there were only 26 examples of it in the entire 450-day dataset. It's like a cold case with not enough clues to solve it. So you might be thinking, okay, that's a cool student project, but why does this puzzle really matter? Well, this investigation, as small as it might seem, actually has some pretty big implications for how we understand our world. What this project shows so perfectly is just how powerful data science can be as a tool for real scientific discovery. It shows how we can take these raw, really complex measurements from our environment and, using these techniques, turn them into genuine, actionable insights that can help us build much better climate and weather models. And that really leaves us with this huge, fascinating question, doesn't it? This was just one puzzle hidden in one forest. As our climate continues to change and as we gather more and more data about our planet, what other profound environmental secrets are just sitting there, waiting for the right digital detective to come along and unlock them?